Hi, I'm Norman Wahlberger. Today we're going to return to the Wild Trig playlist, which explains rational trigonometry to a wide audience. We're going to be going in different directions. We're interested particularly in explaining something called vector trigonometry, and then moving to the very important understanding of three-dimensional and then four-dimensional geometry. These are vast vistas which are waiting for us to explore and develop. Okay, so in our last video in this series, which was quite some time ago now, we were talking about determinants in geometry, and I want to continue with that today. It's a very important theme, the introduction of this very important function, the determinant, into geometry as a core underlying object in geometry. And what we want to do today is connected with fundamental aspects of rational trigonometry. And along the way, I'm going to also introduce some interesting, important new notations that will be very useful for planar geometry. Okay, so I remind you that the basic situation is in fact a very familiar one. We have the plane, we have two vectors, v equals ab, and say w equals cd. And these two vectors here form a parallelogram because we can take this vector and translate it here. We can take this vector and translate it there. That's then a parallelogram. And the determinant, this AD minus BC quantity, is interpretable as a signed area of this parallelogram. This is really the reason why the determinant is so important, because it captures the idea of area. And not just area, in fact, but crucially something called signed area, which we're going to talk about. Okay, very important, so linear or linear algebraic aspect to area with huge consequences, not just for linear algebra, but also for calculus. Okay, so that's a very interesting formula, this one right here, that the area of this parallelogram is the determinant of this 2 by 2 matrix obtained by taking the two vectors and putting the first one on the top row and the second one on the bottom row, a, b, and c, d. And then the determinant of that is, in this case, a times d minus b times c. So this is a number that then measures the size of this parallelogram. And I want to point out that in the special case when A, B, and C, D are in the same direction, in other words, when V and W are multiples of each other, then this quantity is going to be 0. Okay? And in fact, if you think about ratio, the rational number A over B and the rational number C over D, I remind you that those two rational numbers are equal precisely when exactly AD minus BC equals 0. Okay, so that quantity is somehow measuring how far apart these two vectors are from being collinear, or one being a multiple of the other. Okay, so a crucially important formula in planar geometry. So let's think about how we can justify this formula. Given that we have a prior understanding of area in terms of our Cartesian coordinates, and say areas of rectangles and triangles. So we're familiar with the area of a rectangle, at least if it's positioned in the standard way as being base times height. And we have an understanding of the area of a triangle as being 1/2 base times height, at least if the base and the height are sort of aligned in these directions. So we can use that prior understanding to justify our formula. And it's very interesting to do that in actually a number of different cases. So let's have a look at this particular setup here, where we have our vector v, a, b there, our vector w here, and here's that parallelogram whose area we want to determine. Now, I've drawn the line here, and we're going to look at just half of the parallelogram. So this half of it here that's shaded in red. So the area of this triangle is what? So one approach to finding the area of this triangle is to do some cut and paste arguments. We can say, well, we can take the area of this big triangle and subtract the areas of these three smaller objects, then we'll get the area of the triangle that we're interested in. All right, so the area of the big triangle is 1/2 the base times the height, and let's have a look what that is. So if this is the vector AB, then that's A and that's B. And if this is the vector CD, then this is also the vector CD. It means that we're going over C in the X direction and D in the Y direction. So this dimension is C, and so is that one, and this dimension is D. So altogether, the horizontal separation here is A plus C, and the vertical separation here is B plus D, meaning that this entire triangle has area 1/2 A plus C times B plus D. And then we can subtract the area of this little triangle, which is 1/2 AB, the area of this triangle here, which is 1/2 CD, and the area of this rectangle, which is BC. And then when we look at this expression, we see that there's quite a bit of cancellation. The AB times 1/2 cancels with that. The CD times 1/2 cancels with that. The AB is still remaining. No, so the AD is still remaining. And the BC, well, there's 1/2 BC here minus a full BC there, gives us minus 1/2 BC. So what remains after we simplify is 1/2 AD minus BC. So this calculation shows that the area of the full parallelogram is indeed AD minus BC as we've claimed. Now, cut and paste kind of arguments like the one we just had depend on the relative positions of things. And it's interesting to investigate whether the same derivation holds when our vectors v and w are in somewhat different positions. So as an exercise, please show that the same formula actually applies also in these different kinds of situations. If we have, say, vector v down here and w here, or if we have our parallelogram here, v here and w here, or perhaps v here and w here. So by making appropriate subdivisions and comparing them with standard rectangles and triangles whose sides are aligned with the coordinate axes, see if you can extract that the area of the parallelogram in each of these kinds of cases is AD minus BC, assuming that v is the vector AB and w is the vector CD. Now I want to show you how the determinant function is intimately connected with quadrants and spread, our two fundamental measurements in planar geometry. And to do that, I want to introduce the idea of a certain type of rotation in the plane, which is very important for Euclidean geometry. It's really a quarter turn. Okay, so we might call that the perpendicular rotation, and I'm going to give it a particular name that takes a vector v and takes it to what we're going to say is the vector v with a superscript b over it. All right, so that's a transformation from one vector, in this case v in this direction, to vb in that direction. And what is it? Well, it's given by this formula here, that if v is ab, then vb is minus ba. Okay, and this B actually stands for blue, okay? It doesn't have anything to do with the B that's in there, so just pay attention to that. Okay, so for example, if the vector V is 3, 1, then the transformation takes that to minus 1, 3. Okay, the interchange and the this B has a minus sign introduced. So 3, 1 goes to minus 1, 3, and we can see that visually this is a rotation by a quarter turn, or 90 degrees, or pi by 2. All right? And it's a rotation in the positive or counterclockwise direction. When we're talking about determinants, rotation directions matter, and orientation becomes important. And so it's useful to keep in mind this convention that if we're going around in this direction, that's generally considered to be the positive direction, while this direction is the negative direction. Okay, so this transformation is a positive turn of a quarter of a turn, or rotation. This is a very useful trick to know when you're working with planar geometry, that if you're given a vector AB and you want another vector which is perpendicular to it, you can just rotate it by 90 degrees. You can get at that algebraically just by taking AB and turning it into minus BA. But let's convince ourselves that this actually does work. So first of all, let's observe that in fact the quadrants of these two vectors is indeed the same. The quadrants of v is a squared plus b squared, and the quadrants of vb is minus b squared plus a squared, and obviously those two things are the same. So yes, those two vectors certainly have the same quadrants. What's maybe not so obvious is, how do we know that they're actually perpendicular? How do we know that this vector and this vector are always perpendicular? Well, there's two answers that we could give. One is through a little bit of linear algebra. So if you've done some linear algebra and you know about a dot product, you'll know that two vectors are perpendicular precisely when their dot product is 0. So what's the dot product between these two vectors? Between AB and minus BA? Well, the rule is that you take the product of the first two entries, and then you add the product of the second entries. So it's A times minus B plus B times A, and that's obviously 0. And so by the linear algebraic approach, these two vectors are perpendicular. How about if we haven't seen some dot products in linear algebra and we just want to rely on traditional geometry? How can we see that these two vectors are perpendicular? Well, let's just have a look at the points. So here is the vector v ending at the point AB, emanating from the origin. And here's this vector v super b, which is emanating from the origin and getting to minus BA. So let's just consider this right triangle for a second. And how do we detect perpendicularity? Well, we detect it by using Pythagoras' theorem. Right? That's the way perpendicularity manifests itself in geometry. Okay, so the vector joining A and B, that vector there, is obtained by taking the difference between the positions of A and B. So it'll be minus B minus A and A minus B. And if we're interested in its quadrants, we then have to take the sum of the squares of its two entries. So we get minus B minus A squared plus A minus B squared. And then when we look at this, well, this is just the same as A plus B squared. So when we square this and we square this, the two cross terms are going to cancel. There'll be a 2AB occurring here and a minus 2AB that will cancel. And we'll just end up with 2A squared plus 2B squared, which is the sum of this quadrant's, which is A squared plus B squared, and this quadrant's, which is also A squared plus B squared. So yes, indeed, this triangle satisfies Pythagoras' theorem, namely this quadrant's plus this quadrant's equals that quadrant's. That's telling us geometrically that that is a perpendicularity there, or a right angle. Now I'm going to give you a novel but important definition. All right. This is something that you don't see anywhere else. We're going to talk about the cross product of two planar vectors, two vectors in the plane. Cross product. Okay, here it is. If v equals the vector AB and w equals the vector CD, then we're going to define the cross product v cross w to be equal to, well, that same quantity, that same determinant that we've been studying over and over, AD minus BC. In other words, the area of the parallelogram formed by V and W in that order. Really a signed area, to be precise. Now, this will take some getting used to for some people, because if you've taken engineering courses, you're familiar with the cross product in the context of vectors in three-dimensional space. You'll know that if you have two vectors in three-dimensional space and the cross product is a third vector, that's perpendicular to the two vectors that you have. Okay. We are not working in three-dimensional space here. Our vectors are vectors in the plane. And so this cross product is different, but still very closely related, to the more familiar cross product in 3 dimensions. Okay? It's like a baby version of that. You can think about it that way. Okay. So the cross product of two vectors is a number. In fact, it's just the area of the parallelogram spanned by those two vectors. Okay, now I'm going to leave you with a little bit of an exercise to check some basic but fundamental things. That if we interchange the order of the vectors, then the cross product changes sign. That if we take a vector cross itself, we get 0, the number 0. And that the cross product is linear in a kind of an obvious way. That if we take v1 plus v2 cross w, that's the same as v1 cross w plus v2 cross w. And that if we multiply by some scalar lambda v times w, or cross w, is the same as lambda times v cross w. And that's also the same as v cross lambda times w. So these are important properties of the cross product. You might wonder, what about the distributivity in the other direction? Well, if you combine this one with the first one, then you can see that the distributivity also applies to the second variable as well. So there's nothing special about that. Okay, so just a little exercise. Make sure that you check that this very simple but novel definition of the cross product of two vectors has these nice linear but sort of skew symmetric properties. And now let us connect the determinant via this cross product with our fundamental metrical quantity of quadrants. Okay, the result is the following theorem: that if V is a planar vector, say AB, then the quadrants of V is the same as the cross product of V with V super B, where V super B is that perpendicular rotation of the vector V. Okay, well, let's check that. So we know what the quadrants of the vector V is. It's just the sum of the squares of its components. It's a squared plus b squared. And what is this thing? Well, there's the vector V, and there is the vector V super B. There's the perpendicular rotation of V. And if we take the cross product of these two vectors, what do we get? Well, it's AD minus BC, so it's the product of the outer ones, which is a squared, minus the product of the inner ones, which will give us a minus b squared, or a plus b squared. So yes, indeed, the quadrants of AB is equal to the cross product between the vector V and its perpendicular rotation. In that order, there's the vector V, and there's the vector second, that rotated vector. So in determinant form, what we're doing is we're noting that the quadrants of a vector could be written as a determinant. It's the determinant of the matrix that you get by writing down the vector together with its perpendicular rotated vector. That little 2 by 2 matrix, its determinant is just the quadrants of the vector V that we're starting with. In our next video, I want to talk about spread, which is the more novel aspect of rational trigonometry, replacing angle, and how that is also intimately connected with the notion of a determinant in a way that, in fact, we've seen before, but which also has interesting manifestations in the other geometries. So I'll remind you a little bit about chromogeometry, and not just the blue, but also the red and the green geometries, and how we get a kind of uniform understanding of spread and the relation with determinant. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.